Hi, the lecture today is titled the Mean Value Theorem. In this section we are going to learn a few theorems that have a bit of a philosophical bent. They are mostly about assuring us about certain events without telling us exactly how that event is going to occur. We are going to take a look at the theorems and some of the applications. We are not going to go through the detailed proof of it. That is a topic taken usually in advanced calculus class. The first of these major theorems is named after Rolle. So we have Rolle's theorem. It's a very simply stated theorem. It says that if you have a graph that starts at a certain elevation and then comes back to that elevation, then at some point it has to turn around. So you might think that's pretty obvious. Let's go ahead and draw such a graph. Here, say, is our starting point. Our requirement is that the end point will have the same elevation. And then we have a graph that starts at here, goes up, and say it turns around and comes back here. Rolle's theorem says that if this function is continuous from here to here and it is differentiable on this interval, then there is some point in between at which the derivative is going to be 0 or tangent line is going to be horizontal. Well, where is it? In this picture it looks like it's somewhere around here. Rolle's theorem doesn't tell us where that's going to happen, but it just tells us there is a point at which the tangent line becomes horizontal. So what are the properties again? Here is our function y equals f of x. It is defined on an interval that stretches from, say, a to b. So let's write this thing down. Consider y equal to f of x defined at least on interval from a to b, perhaps it stretches beyond these 2 points, with the following restrictions. First of all, the elevation at the beginning, at the end, and the end are the same. These start and end at the same height. The function f is assumed continuous on that interval from a to b. I'm going to explain shortly what does it mean to be continuous, but next property we require is that the derivative of the function exists on the interval f prime exists on the interval from a to b, not necessarily at a and b themselves, but just inside from a to b it exists. So we have a function that is defined here, first and last point at the same height. It is continuous throughout, and its derivative exists on the open interval. Then there exists c in the interval from a to b. So there's c somewhere. Here's the c. Here's a point c somewhere in the interval such that f prime at that point is 0, or in other words, the function has a horizontal tangent line at that point. To digest this theorem, we have to go do several things. One thing we can do is to drop some of these requirements and show an example that the conclusion is not going to happen. That is going to show to us that these are essential requirements. And then we are going to take several different shapes to see where C might show up, or if there are several candidates for C, and so on. Let's go ahead. Well, if the first and last point are not at the same height, it's not required that the function will have a point at which the derivative is 0. Here's a simple example. I draw a function that starts here and goes somewhere else. There is no reason for it to be having a turning point in it. If your start and end are different elevation, you are not forced to be turning around. So there is no such C in this case. Why do we insist that the function has to be continuous? Well, what does it mean to be continuous? Simple explanation of continuity is that your hand has to stay on the page, or that the function cannot have a break in it. Here, let's go ahead and drop this requirement and see that the conclusion again would not be valid. Here I draw another function. Here's my coordinate axis. I start at this location. Perhaps go up here, and let me do a better job. Here I start at this location, go up, and then perhaps I make an empty spot here and come back up to the same elevation. So beginning and end have the same elevation here. It's just the function is not continuous. How did I prevent it from being continuous? I created a break in it. I go up to this, make a jump, start at here and go up. Again, you don't see any point at which the derivative is 0. You don't see any horizontal tangent line in it. Okay, let's go assume a situation where these two are there, but the derivative fails to exist. See what's going to prevent perhaps existence of such a point. Here's an example. I start at this point, perhaps go up, here I come back down. So start and end are at the same elevation. I'm continuous. Here I drew it by holding my pen to the page. There is no point at which the derivative is 0. Notice here the derivative is perhaps 1 all the way through, and all over here the derivative perhaps something like -1. At this point the derivative does not exist. The function has a sharp corner at this point. So these three examples show that these assumptions that we are using here, they are all essential. Of course the function better exist also. If it doesn't exist, there isn't anything to talk about. So these are all essential requirements. Okay, that was a statement of Rolle's theorem. Statement of some of the problems ask you to find C in a particular example. Usually there's a luxury you don't have, but if the function is very simple, you can go ahead and find this C. All that you have to do is to take a derivative, solve this thing, and make sure that you picked up one of the solutions which is sitting inside this required interval, and that's all. Notice that we are not saying that there is only one such C. There could be plenty of them. So We are not being stingy in that regard. When you say there exists a C, we are not saying that there exists only one C. There could be many of them. Here's an example. Suppose this is my starting point, this is my ending point. I could have as many turning points as I wish if I wish to arrange for it here. In this case, we have one C here, so you can call it like C1. Another point here is C2. Another point here is C3. Another point here is C4. There are 4 points at which the function had a horizontal tangent line. Any of them, for example, here the function has a horizontal tangent line, here also, and here is another example. Here's an example. Suppose I give you a function. Consider f of x is equal to x squared minus 6x plus 7 on the interval from, say, 0 to 10. Show that the requirements of Rolle's theorem are satisfied and find point C, perhaps several points predicted by that theorem. So first of all, this function exists everywhere. It's continuous everywhere. It's differentiable everywhere. Its derivative exists. So all requirements are easily satisfied. How do I show that the conclusion also is valid? Well, all I need to do is to take a derivative of this thing, f prime of x, set it equal to 0, x is 2x minus 6 is equal to 0. That tells us that x is equal to 3. This is a point at which the derivative is 0, and I forgot to insist on something before I go further. Let me make a correction to what I just mentioned. Here I had to excuse me. There was one requirement that was not as trivial. I have to check that. Let me write that first. These requirements, the function is continuous, its derivative exists. We have to check that the function at the first and last has the same height. We go ahead and check that here. What is the value of the function at the beginning? Our beginning is 0, f of 0. If I put 0 in this thing, obviously I get 7. At the last point, f of 6, 6 squared is 36. 6 times 6 is also 36, and then plus 7 is equal to 7. So what we have is that f of 0 is equal to f of 6. Typically that's the only item you need to check. So at the first and last point, the value of the function is the same. So whatever the function is going to do, which is in this case, the function is going to descend, start to descend at 0. At 3 is going to turn around, come back to the same height as 6. So what we did was we took a derivative, set it equal to 0, solve it, we got the value x equal to 3, we make a note of the fact that 3 is a member of this set from 0 to 6. So 3 is a point that sits in interval from 0 to 6. So the point that is predicted by Rolle's theorem in this particular problem is just c equal to 3, and then we are all done. Now there is a slightly more advanced version of Rolle's theorem, which is where we get the title of our section, and that's called the mean value theorem. So we go ahead and write the mean value theorem. And that is slight generalization of this, the kind of sense that maybe this is not so essential. What if the beginning and last point are not at the same altitude? Can we still come up with a theorem similar to this? And the answer is yes. Here is how the setup goes. Suppose a function that is continuous and differentiable starts at some point. So I start at this point, and I don't end up at the same altitude, I go some other point. The function is assumed continuous and differentiable. So for example, it could be like this. This software is not cooperating with me today. Well, we are no longer claiming that there is a horizontal tangent line, but we can make a different kind of a claim, which is the following. If I draw a line connecting these two, the beginning and the last point, can you guess what we can say about this function in connection to this I don't know what color it is, a purple color line? There is a point on this function where the tangent line is parallel to this line that connects the first and last point. This is called the secant line. This is called the secant line. We are claiming that on this arc there is a point at which the tangent line is going to be parallel to this secant line. More or less in this example, the tangent line is going to be seated here. So we can write that theorem one of two ways. One of them is this. Suppose f exists on interval from a to b, f is continuous on interval a to b, f prime exists on interval from a to b, not necessarily at the endpoints, then there exists point C inside interval from a to b such that tangent line, at C is parallel to secant line connecting the endpoints. Another way we can state the conclusion is that at the point C, the derivative, or the derivative at C is equal to, remember, derivative at this point is going to be same as the slope of this line. So let's go ahead, remind ourselves, here's the point A, here's the point B. This is my point C. Slope at this point, or slope of the tangent line, is f prime of C. What is the slope of the secant line? Well, to find the slope, I have to divide the rise divided by run. How do I find the run? Run is from A to B. Run is just B minus A. What is the rise from here to here? Well, at A, the height of the function is f of A. At B, the height of the function is f of B. If we go from this to that, our rise is equal to f of B minus f of A. So what is the slope? The slope the ratio of rise to run is going to be f of B minus f of A over B minus A. So our statement is that this slope will be same as this slope, or f prime of C is going to be equal to this fraction, the formula for the slope. So there exists a C inside this interval such that the derivative at that point is equal to the difference of the function at the endpoints divided by, correct my handwriting here, that's A, divided by the run, which is B minus A. So as you see, it's a simple observation. The proof of it is very simple once you accept Rolle's theorem. Essentially what you do is that you take the function over there and subtract this other one from it, and you get another function to which you can apply Rolle's theorem. Let me tell you that Rolle's theorem is actually the same as the mean value theorem. Here f of B minus f of A is 0. So all that you're saying is that the slope of the secant line is 0. There is a point at which the slope at that point is also 0. Now we are saying that in general secant line could have any slope, and the claim is that there is another line, there's another tangent line whose slope matches this secant line. Let's go ahead and do a simple case. For example, here's a question. Example. Consider f of x equals to x cubed plus x minus 1 on interval from 0 to 2. Show that mean value theorem is applicable and find the point C that satisfies the statement theorem. Okay, here's a function. We don't really need the graph of it, just know that we need to find out the slope of the secant line and show that there is a point in between where the slope of the tangent line here is going to match the slope of the secant line. So what is the starting point? Starting point, x is equal to 0. So what is f at that point? Or again, to make it look like what I wrote there, r. A in this case is 0. What is f of a? Our a starting point is 0. If I plug 0 in this, I get -1. The end point we called it b before, b is equal to 2. What is f of b? Let's plug 2 in this. 2 cubed plus 2 minus 1, so that makes it 9. So slope of secant line that connects the first and last point, remember that was f of b minus f of a over b minus a. That makes 9 minus -1 over 2 minus 0, that is 10 over 2, that is 5. That's the slope of the secant line. That's the slope of this line. What is left to figure out? There is a point where the tangent line is going to be parallel to this. Well, how would two lines be parallel to each other if their slopes are the same? How do we find the slope? Well, we take a derivative. Let's go back here. What was our f? F was x cubed plus x minus 1. To figure out the slope, I need the derivative. Well, what's the derivative? Derivative is 3x squared plus 1. Is that right? The derivative is 3x squared plus 1. The derivative gives us a slope of tangent line. If this slope wants to match that slope, that's going to force an equation on top of us. So 3x squared plus 1 has to be equal to 5 for the two lines to be parallel to each other. I solve this equation. So 3x squared is equal to 4. So that gives us that x squared is equal to 4/3. What does that give us? That gives us x is one of two answers, plus or minus square root of 4/3. If you wish to clean up, plus or minus of 2 over square root of 3. The claim of mean value theorem is that there is a point that sits inside of the given interval. So which one of these two sits? 2 over radical 3, that is almost 1.1. So we are going to declare the positive answer here as our correct answer. Check that it really sits on the interval that was given at the beginning, and then we are all set. So here is our final answer. We have found the point which tangent line is parallel to the secant line. Okay, there are a couple of corollaries of these theorems that are going to be very important for us at the end of this chapter. So we are going to write that down. So corollary is something that you conclude from something else. You might call it a corollary, you might call it a theorem. Depends on how important it is. It's very important. You call it a theorem. If you want to consider it of having a less importance or immediately coming from something else, you call it a corollary. Here's a theorem. If a function f is such that its derivative is 0 for every x in an interval from a to b, if the derivative of a function is 0 everywhere, what do you think you can conclude? Pause for a moment and think for yourself. If a function exists from a to b, so our assumption is that, assuming f exists on, just like all the previous problem, from a to b, the function is defined, or perhaps defined even beyond that. What do you conclude? Did you make your guess? Well, the function is going to be constant all over that interval. Then f of x is constant on interval from a to b. Let's think about it. If the derivative is 0, means the function is neither going up nor is it going down. And this is happening at every x. So suppose you are starting at here. Derivative is 0, so you have to stay horizontal. You come here. The derivative is still 0. You have to stay horizontal. The derivative is still 0. So you are never given a chance to go either up or down. So our claim now is that if you had started at point A and end at the point B and derivative is 0 everywhere in between, the function is going to be some constant k that is going to give the definition of the function. Why is that so? Well, by mean value theorem, f of, let me just pick some x here and apply the mean value theorem. Pick an x here, apply the mean value theorem on this function between a and x. What does the mean value theorem say? It says f of x minus f of a over x minus a is equal to the derivative of this function at some point between a and x. So if I've chosen a and x arbitrary, then there is going to be some point c, we don't know exactly where, but some point c in between where this relationship holds. Well, if that is the case, I'll come and say, you told me the derivative of this function everywhere is 0, so that tells me that really f of x minus f of a over x minus a is 0 regardless of what x I choose. This right hand side will be 0. If a fraction is 0, its numerator has to be 0. If the numerator is 0, that tells me that f of x has to be same as f of a. That is, at this point, function is forced to have the same height that it had at the beginning. Since x was arbitrary, I can do this with respect to any of these points, anywhere at all from beginning to end. I have to have the same height that I have at the beginning. And that's exactly what it means to say that the function is constant. So the function is going to be constant everywhere. So that is one theorem that's going to be very important later on the section on integration, we are going to face this issue. If the derivative of a function is 0 over stretch, the whole function had to be constant on that. It's quite intuitive, and here is a short proof of it. Another similar theorem or corollary is that if the derivative of a function is equal to derivative of some other function, if the derivative of two functions match each other on every point of a certain interval, not just one point, but all over an interval, the two derivatives are the same, what do you think we can conclude? Let me ask you to go through an exercise. Here, x squared plus 5, say. The derivative of this is same as what other function's derivative? Let's just come up with a conclusion or exercise by ourselves. On the left hand side, I have a function, I'm differentiating it. On the right hand side, I'm asking you to find a function whose derivative matches the left hand side. Can you think of any such function? Maybe you can pause for a moment and come back and tell me what you found. So what did you find? It's quite easy. The derivative of this becomes 2x. It doesn't matter what number you had here. So if I have some other number, it still works, like x squared plus 11. The derivative of this thing matches that one. Notice that the difference of these two functions, just the difference of these two constants, and that's what the conclusion of this theorem is. If the derivative of two functions match each other on an interval, then, so here's a continuation of the theorem, then f of x minus g of x is a constant on that interval. Or if you wish to express it differently, then f of x and g of x differ by a constant on the interval from a to b. There is still another kind of a terminology they use. We kind of like to say these two functions are equal, but obviously as you look at it, they are not quite equal. The x portions are equal. The constants are different, could be different. So the way we can say this thing is that f and g are equal up to a constant. F and g are equal up to a constant. Okay, so that is another major theorem from this section. We are going to put it to good use, and let me go ahead and do some problems, example of some problems that on the first look they might appear not to have anything to do with these theorems, but they actually have everything to do with them, and the theorems come out and be very useful and helpful for us. Here is one example of such problem. Let's it says show that the following equation, x to the power of 4 plus 4x plus some unknown constant equal to 0 has at most 2 real roots. Okay, what's the issue here? When you solve an equation can have many roots. Sometimes you want to count to know how many roots there are. On the other hand, we know that an equation that is of degree 4 can have up to 4 real roots. It always has 4 roots, but some of them might be imaginary roots. This one is saying that regardless of what constant you choose here, this equation is never going to have more than 2 roots. For example, it's not going to happen that it has 3 real roots. It doesn't happen that it is going to have 4 real roots. It either has 2 or 1 or none real roots. Now, you can experiment with this problem several ways. Like you can choose different numbers, graph y is equal to this, see how many roots you get. You can change the constant and see what happens to your graph. Evaluate it and experiment with it to see how does that relate to the problem that we have at hand. But let's go ahead and see what's the connection with the mean value theorem we have here. Suppose you were to graph this function y is equal to x4 plus 4x plus c. Well, when you are graphing it, what's going to play the role of a root on a graph? If you draw this function and it looks like this, for example, well, the point of intersection of the graph with the x-axis, that's exactly where the root is going to be, because at these points y is equal to 0. What we are claiming in this problem is that regardless of what kind of a constant c you put here, you are not going to see a picture perhaps looking like this. It doesn't crisscross so many times that it never going to happen that you have, for example, 4 intersections. This does not happen, we are saying. It's going to happen more or less in this style. Well, once again, I recommend that you go ahead and pause and try to come up with a reasoning yourself and then come back here. Okay, I go ahead hoping that you have made an attempt yourself. Maybe you want to go ahead and look at some of the problems in the text itself, see if it helps you. Here, I go ahead and take a derivative of this function y prime. The derivative of this is going to be 4x cubed plus 4. But setting the derivative equal to 0 is going to tell me all locations where the tangent line is going to be horizontal. Well, this is going to tell me 4x cubed is equal to minus 4, which tells me x cubed is equal to minus 1. X cubed equal to minus 1, the only real root of it, what's the only real root of this? It's just minus 1. There is no other real root. What is the importance of the fact that we got only one answer? The fact that, so let's write, we got only one point at which derivative is 0. Well, what's so big deal about the derivative being 0? That means there is only one point at which, or only one point at which tangent line is what is horizontal. There is only one point on the graph where the tangent line is horizontal. Well, how does that rule this one out? If you crisscross so many times, for every 2 consecutive crossing, you are going to have one point, by the Rolle's theorem, you're going to have one point at which the tangent line is horizontal. Is that so? If you cross here and here, automatically, by Rolle's theorem, somewhere you are going to have zero derivative. And then if this happens again, you are going to have another points at where tangent line is horizontal, and then again another one. So if you are given only one point where tangent line is horizontal, it had to be a picture like this. Okay, so that had to be -1. So this axis turns out has to be on the right hand side if this happens. So the function could not cross more than twice. It's also possible it didn't cross at all. For example, the function could have looked like this. Tangent line is horizontal at some location without it ever even touching the x-axis. We are not ruling that possibility. In fact, if you choose a large enough c, your function is going to sit high up and is not going to have any crossing or any roots at all. Notice the flavor of this problem is so different from the other problems you had before. We are assuring ourselves of a certain event without giving specific numbers or locations or anything. What did this problem say? It's just saying it has at most 2 real roots. It's not helping us to find them really. Finding them exactly is going to be a really tough job. Finding them approximately is not such a big deal. Now you go ahead and do several problems from this section of the same flavor. Again, just try to absorb what is involved here, and we are going to be passing this and going on to items that are perhaps more to your liking and more formula oriented, as we are going to see in section 4.3. Okay, good luck and God bless.